Welcome to e-Padasala lecture series in computer science. In this module, we are going to discuss a new design paradigm called transform and conquer. Probably you can recollect in the earlier modules, we were discussing about a design paradigm called decrease and conquer. As part of that, we discussed various algorithms. In this module, we are going to discuss a new design paradigm called transform and conquer. This is a variant of divide and conquer algorithms. So, in this particular module, we are going to discuss about some of the basics of transform and conquer paradigm. We are going to discuss about various matrix operations like matrix inverse and matrix determinants, and the main objective of this particular module is to discuss how these problems can be solved using transform and conquer. As part of that, we are going to discuss about the Gaussian elimination method, using which we can write better algorithms for solving matrix operations. So, what is transform and conquer? Transform and conquer is a two-stage procedure where we are trying to transform a problem into another problem that is more amenable for solutions, and once we transform a problem to another problem, we can solve the new problem which is in a convenient form. Once we solve the new problem, the solutions can be transformed back to the solution of the original problem. What is the necessity for this? The necessity is that sometimes the problem posed may not be suitable for direct solving. In that case, perhaps we may have to convert that problem into some other problem which may represent the convenient way for solving, so that this paradigm can be effectively utilized. So, we will take some small example. Let us assume that we are given two integers. So, it is given in the Roman numbers. So, suppose if the problem like this is given, so we have to solve this, and we are not very much comfortable with the Roman system. So, we can apply the transform and conquer strategy. So, we can convert this problem into another domain which is very convenient for us, that is in the Arabic system. So, we can convert these numbers as 12 into 4. So, now this problem is very much familiar for us because we are very much comfortable with the Arabic system of numbers. Now, we can multiply, and once the multiplication is done, we can convert that back into the original domain. So, this kind of paradigm is what we are calling as the transform and conquer paradigm. Sometimes this paradigm can yield very sophisticated algorithms. Let us take one example of convolution of two signals in the spatial domain. Convolution, as we discussed in one of the earlier module, involves shift and addition operations. So, it is a very complicated procedure. So, what we can do is we can transform this problem to the frequency domain. In one of the earlier module, we discussed about the fast Fourier transform, using which we can convert the signal information from the spatial domain to the frequency domain. Once we have the data in frequency domain, the convolution is reduced to ordinary multiplications. So, now we can solve the new problem by simply multiplying, and once we have the resultant, we can transform that back to the spatial domain by applying the inverse fast Fourier transform. In this particular manner, we can easily develop algorithms. In this way, we can develop faster algorithms which are more required for modern applications. Similarly, sometimes we may not have algorithm for one particular problem. In that case, we can change the problem to some other problem for which we have an algorithm. For example, you consider the problem of let us say LCM. Let us assume that the algorithm is not available, but let us assume that we have the algorithm for GCD. If this is the case, then we can easily convert the problem of LCM finding to a problem in that involves GCD. In this particular method, using this problem reduction mechanism, we can develop sophisticated algorithms. In other words, in this design paradigm, so we deal with some of the transformations. The transformations can be something like the instance simplification, where we try to reduce the instances that are more amenable for solving, and once the problem is transformed, we can solve that. In some cases, we require some sort of a representation change, where we change the representation of the problem and we can solve it. In some cases, we go for some sort of a problem reduction methodology. These three represents the variants of the transform and conquer strategy. In this particular module, we are going to discuss about the instance simplification, where we are going to bother about the transformation of problems using the instance simplification method. So, let us discuss some of the algorithms for explaining this particular strategy. One example of this is called the presorting method. Presorting method problem can be formally stated like this: given a random list of numbers, we have to check if there are any duplicates. Duplication checking is one of the application of presorting, where we can sort the elements to check for the duplicates. How can we check the duplicates of numbers? So, for checking the duplicates, we have to compare every pair of numbers, and if comparison gives the same result, we can conclude that there are certain duplicates. We can solve this problem in the conventional manner using this informal algorithm like this. So, take any element x of the list A, then check for that particular element in the list. That list is going to be A minus x, and if x is equal to y, then we can say that the elements are not going to be unique. Otherwise, we have to say that there is a duplicate element that is present. This sort of brute force technique involves comparison of every element with every other element that is present in the array. So, this leads to the order of n square algorithm, and we can simplify this problem using the transform and conquer technique, where we can sort the elements, and once we sort the elements, the advantage is very simple. I have to compare only the adjacent elements and not all the elements of the entire list. So, this is going to be the formal algorithm of presorting. So, you can see exactly what is happening. In the first step of the algorithm, I am going to sort this, then I am starting one loop from 1 to n minus 1, and you can see very well, since the elements are sorted. So, all I am going to do is I am going to check only the neighboring elements, and if the neighboring elements are same, then we are going to send the message that this is not going to be unique, otherwise we are going to say that the elements are unique. So, this is what the pre-sorting algorithm for checking the duplicates. So, you can see very well this is what the algorithm is, and you can see that the uses of this pre-sorting is searching, we can check this sort of element uniqueness, etc., etc. Okay. And we can also use this for searching. So, you can see exactly what is happening now. So, if I want to search, I can sort this by means of the merge sort, and I can apply the binary search because the elements are already sorted. The efficiency of this algorithm is what is a theta of n log n, which is a requirement for the merge sort, and binary search requires the order of n log n. So, you can see exactly that the complexity of this algorithm is theta of n log n. So, this is the another case, again you can see that the complexity analysis is going to be theta of n log n. So, in terms of computational complexity, fine, we do not have too much gain, but nevertheless this represents some of the simplicity of the given algorithms. So, this is the algorithm, formal algorithm for checking the what is a element uniqueness. So, you can see exactly the real advantage is I can compare only the adjacent elements and not anything else. Another good example of transform and conquer is computing mode. So, what is a mode? Mode is a statistical operation which represents the value that occurs most often in a list of numbers. For example, if I take a list like this, you can see that the number that frequently occurs in this list of number is 5. Therefore, the mode of this particular list is 5. And if there are several different values occurs most, then any one of the values can be considered as the mode of that particular list. Fine. How to solve this problem? The simplest brute force technique is very simple. Take the list and find the frequencies of every element, and we have to output the number which occurs most, that represents the counting approach. So, you can see that the steps of this counting approach is like this. In step 1, we are going to find the length of the list A. So, we are finding the length and we are setting the frequency from 1 to max, and for each element I am traversing the entire list making a count. So, you can see that it is getting incremented, and once I have the frequency, then I have to find out the number that has got the maximum frequency. So, in step 4 I am just assigning the first element of the frequency list as the potential mode, then I am starting a loop from 2 to max, and I am comparing the frequency of every element with this particular mode, and if the frequency is going to be larger, I am taking that particular index. And finally, once I come out of this particular loop, then the variable mode will have the value that occurs the most, and I am going to return this. So, this is the traditional brute force algorithm for finding the mode. Now, we can condition this problem suitable for transform and conquering approach. So, what we can do is, like our pre-sorting, we can sort the elements. So, now the advantage is very simple. Once we sort, all the elements that are similar will come together, and once we have the togetherness, we can easily increment by maintaining the run length. So, this is the advantage. As the earlier problem, the computational gain is not going to be very much, but the advantage is we do not have to search for the number in the entire list, but instead we have to search only in the adjacent positions. So, this is the algorithm of what you say mode finding. So, sort A. So, you can see that the variables are assigned. I am starting the loop and I am going to find the run length. So, I am starting the loop as part of that. If the element is present in the adjacent locations, I am going to increase the run length, and if the run length is going to be greater than the frequency, I am going to update the frequency as well as the mode value. So, at the end of the algorithm, fine, I have the mode value and I can return this as the resultant of this particular procedures. So, in short, I can summarize that the advantage of this transform and conquer is that we can have some algorithm which represents the convenience. Okay. So, using this particular methodology, we can solve some complicated problems. Some of the complicated problems we are going to deal with are the matrix operations, especially the inverses and determinant. You know very well that if the matrix order is very high, finding the determinant and matrix inverse is going to be a very difficult task. But these algorithms are so essential for many scientific applications, therefore, we need to develop some faster algorithms. So, we can develop the faster algorithms as part of this paradigm by transforming the problem of finding matrix inverse and determinant to some convenient instance that involves the procedure called the Gaussian elimination. Gaussian elimination problem is very simple. We are given n linear equations with n unknowns with a arbitrary coefficient matrix. So, as this design paradigm suggests, we have to transform these equations into a set of equations with n unknowns with a upper triangular coefficient matrix. And once we have the upper triangular coefficient matrices, we can use the back substitutions starting from the last equations and moving to the first one, we can find the unknowns. So, in this particular manner, the system of n linear equations with n unknowns can be easily solved. So, the strategy is like this: whenever we have to find a solution for inverses, so we are trying to transform that problem into some other problem using the method of Gaussian elimination, so that the problem will be amenable for solutions. So, let us discuss about what you say Gaussian eliminations. As you know very well, so take a simple two equations with two unknowns. Suppose if equations like this are given, then I can find the unknown x. Then once I have the unknowns, then I can substitute that in the first equation for finding the resultant unknowns. So, this is what I do. So, graphically this is what will happen. So, these are the kind of solutions I will get. If there is an intersections, I will have the unique solutions, and if the lines are going to be what is say parallel to each other, then there are no solutions at all, and if they coincide exactly, then you will have the infinite solutions. So, solving two equations with the two unknowns is going to be a very easy task, but this is not the case if we have n equations with n unknowns. So, in this case fine, we have these sort of n equations with unknowns. So, we can't attempt to solve this problem using the traditional method. So, this is where the Gaussian elimination is fit in. So, what we are going to do is we are going to transform this problem into a problem where we are going to get the upper triangular matrix, and once we have that we are going to solve that. So, what this method is going to be? So, the method that is named after the Carl Gauss is going to do something like this. So, it takes the n linear equations and it tries to attempt what you say a21, a31 up to an1. So, the transformation is going to be something like this. Then we are going to keep this a22 and we are going to eliminate all the corresponding coefficients in other equations. Continuing in this particular manner, so the last equation is going to be what you say a(n)n xn is equal to bn prime. So, now this is what the transformed problem is going to be. Now, you can see very well, now you have a upper triangular matrix, so which is more amenable for solutions. Now, I can use the back substitutions and I can solve this problem. So, in matrix form I can represent the previous case as what is a problem of transforming A x equal to b to another problem of A prime x equal to b prime, where A and b are going to be matrices like this. So, this is the matrix formulation of the Gaussian elimination problem. So, what is the procedure? So, the procedure is going to be very simple. So, we are interested in finding the upper triangular matrix. So, upper triangular matrix is the matrix where we have zeros in the lower triangle of the matrix. So, once we have this, then we are going to solve the last equation and we can substitute that value into the equation that comes after the last equations, and the process is continued till the first equation is solved. So, for this we have to do some manipulations. These manipulations are called the elementary operations. The elementary operations that are involved in Gaussian elimination are going to be like this. The first operation is called exchanging operations, where if we have two equations like this, x plus y equal to 3 and 2x plus y equal to 4, then we can interchange these two equations like this. So, exchanging equations are necessary to avoid zero coefficients and coefficients that are of very least value. Second operation is going to be exchanging operation with non-zero multiples. For example, we can multiply the equation throughout by a constant, or we can divide the entire equation by a constant, something like this. And thirdly, we can replace one equation by a multiple of another equations. For example, in this case you can see that R1 is multiplied with constant 2 and row 3 is added to give the resultant new row called R2. So, this is what the elementary operations are. So, once we have these sort of operations, then we can define what the Gaussian elimination is going to be informally like this. So, we are given n linear equations. So, convert that into a matrix notation. So, write the matrix A and have the vector B, which is going to be the RHS part. Then do something called augmentation, where the vector B is added to what you say appended to the matrix A, and once we have this augmented matrix, then we can keep A11 as the pivot element, and having this as the pivot, we can eliminate all the corresponding coefficients of the other equations, and after that we can use the same principle to remove all the redundant coefficients, so that we can have some sort of a upper triangular matrix. So, we will take one numerical example to illustrate this. So, let us assume that we are given 3 equations with 3 unknowns like this. So, now you can see that the first step of Gaussian procedure is we have to augment. So, you can see that the matrix A is going to be 3 1 1, 6 4 1 and 1 1 1, and matrix B is going to be 11 29 and 7. As said earlier, the first step is going to be the augmentation, where we are going to augment this vector B to the matrix A. Now, this is the augmented matrix. So, now the objective is very simple. So, we have to keep the element 3 as a pivotal element, and somehow using the elementary operations we have to remove 6 as well as 1 in other equations. So, that means now you can see that we can use some sort of a transformations like this. The new rho 2 is going to be rho 2 minus 2 into R 1. So, that means you can see that 6 minus 2 into 3 becomes 0. Similarly, you can see that the transformation of R 3 equal to R 3 minus 1 by 3 R 1 is going to eliminate the value of 0. So, now you can observe that the coefficients in the last 2 equations are getting eliminated. Now, we can continue the procedure, and we can keep the coefficient 2 in the second equation as constant, and we can attempt to remove 2 by 3 of the third equations. Now, you can see that the transformation that we are going to use is R 3 equal to R 3 minus 1 by 3 into R 2. So, now you can see that by applying these transformations, now we have the what you say the upper triangular matrix. Now, you can see that the last equation is very easy to solve, that represents x 3 equal to 1. So, that means you can see that what you say x 3 equal to 1, and once you find the value of x 3, you substitute in the penultimate equation. So, that means it becomes 2 x 2 minus x 3 equal to 7. Already we know the value of x 3. So, we can find the value of x 2, and once we know the value of x 3 and x 2, we can substitute that into the first equation. So, that now we have the value of what you say x 1 equal to 2, x 2 equal to 4 and x 3 equal to 1. So, this is the method of the Gaussian eliminations. In some cases problems may come, for example, the coefficient may be 0, and sometimes the number will be very little. So, in that case if we substitute that into the elementary operations, it may yield large numbers. So, in that case we go for the concept called pivoting, where we are going to exchange the equations, or we are going to replace the equation with the non-zero multiple. So, this is the formal algorithm for getting the upper triangular matrix, and this is the formal algorithm for the backward substitutions. The complexity analysis of this algorithm is going to be theta of n cube. So, that means you can see that we can implement this algorithm for reasonable large size of equations. In short, the summary is like this: transform and conquer is a very effective design paradigm. So, which is helpful to transform a problem from one domain to another domain. Matrix operations represent an important class of operations in scientific applications where transform and conquer can be effectively applied, and the first step of this transformation is Gaussian elimination, which is a very effective technique that uses the transform and conquer approach. Thank you very much. Next module we will discuss about how to apply this procedure for solving problems like matrix inverse and determinant. Thank you very much.